Okay. I recently had a couple of conversations about linear algebra and physics. As it turns out, a lot of people are put off by linear algebra and physics. It's important to note that this is actually not a new phenomenon, though the applications of what we today call linear algebra and physics goes all the way back to, a couple of centuries ago, most notably when Euler demonstrated that you can model any rotational motion using matrices, the orthogonal matrices. Um, the application did not really gain much momentum until recent years. Not many physicists were intimately familiar with linear algebra. That's a very interesting example of this that I spoke about, which was when Heisenberg invented what we today call matrix mechanics. He seems to be quiet. He seems to have been quite in the dark about certain fundamental concepts of linear algebra. So Heisenberg was studying along with Max Born and Pascual Jordan about what would later be called matrix mechanics. And all that Heisenberg could do was, he said that he was investigating something quite deep. Heisenberg, he was trying to determine, according to him, the rational basis for the strange observations of quantum theory. And he concluded that the rational basis comes from the following, that quantities that were represented by numbers and were very simply defined in the old in classical mechanics would be replaced by mysterious abstract quantities that followed the strange rules of multiplication, in that they did not follow the commutative law for multiplication. All right. Now, those of you who have studied high school physics know that there's really nothing mysterious about such quantities. We know that matrices do not follow the commutative law of multiplication, but this did not occur to Heisenberg. This is how he put it initially. He had taken a look at the differential equations that Schrodinger had created, and eventually said, oh, well, it looks like if I equate the eigenvalues with the differential operators, then you can see that they behave in this strange way, in that whereas the values, the numbers follow the commutative law of multiplication, the differential operators do not. And so he said, we're basically replacing simple quantities like energy and momentum and other things with abstract quantities that multiply in this very strange way, that follow these strange rules of algebra. Well, Max Born and Pascual Jordan, who are working with Heisenberg on this, pointed out, this is just matrices. Matrices follow this strange law of multiplication, and there's nothing strange about it. Matrices have been studied for close to a century by now, more than a century now. And perhaps you can think about, perhaps there's some meaning to the various entries in these matrices representing the quantities that quantum mechanics is concerned with, what we today call observables. And that is what precipitated matrix mechanics. In fact, Born was quite bitter about it later on. He felt that he and Jordan did not get sufficient credit for having helmed matrix mechanics alongside Heisenberg. And so if you ask anyone today, matrix mechanics is immediately only associated with Heisenberg. In any case, if you also if you there's there might be some evidence to refute what I've just said about Heisenberg's being in the dark about matrices, but there is further support to this idea given by Heisenberg's famous book, The Physical Principles of Quantum Theory. It's a little tiny booklet. Anyone can read it. I'm not recommended it to anyone. It's not necessarily easy reading or interesting reading or engaging reading for most people. In any case, in this book, Heisenberg proceeds to talk about the role of linear algebra in his formulation of quantum theory. And he makes an interesting remark. He says, quantum theory has a lot in common with the theory of relativity, in that both of these have linear algebra in their foundational logical structure. Matrices play a fundamental role in both of these. Of course, that's true. That's definitely true. In special relativity, you have the Lorentz transforms and the associated groups. And in general relativity, again, there is linear algebra exists in the form of tensor calculus. But this is not something that is taken very seriously by most commentators on the subject and by teachers and masters of exposition on relativity. It is regarded, linear algebra is taken to be quite a commonplace element of mathematical physics. Not so by Heisenberg. He thinks it's very curious that both of these theories incorporate linear algebra in a very fundamental way. In any case, that is evidenced by this remark. Okay, in any case, what I was going to say was ultimately linear algebra being a powerful mathematical tool is logically not supposed to be a surprise to someone. So I was only recently alerted to the fact that there's been quite a bit of work done by scientists, mainly mathematicians, working in the so-called theory of computation, in which they cast the models, the most abstract models of logic and mathematics, mathematical calculation, the most powerful mathematical productions into the language of linear algebra. It turns out that linear algebra is sufficient and broad enough to encompass all of computation. The most general and most complete models of computation produced by, Alan Turing and Alonzo Church, and all of them are already encompassed in the ideas of linear algebra. Important fact and very interesting fact. And it has quite a deep import, because if someone tells you that they have discovered that such and such phenomenon can be modeled by linear algebra, there is a chance, a non-zero probability, that what they're saying is a truism. That is, they're not saying anything at all, in a manner of speaking. There is a chance that what they're saying is belongs to the class of statements that Wolfgang Pauli called not even false, right? And because the Church-Turing thesis states, asserts that everything that can be modeled by man can be modeled by a Turing machine. And the recent effort alerted to me by a paper, brought to my attention by a paper by Lance Fortnow, check it out, is indicate that, the Turing machine in and of itself can be simulated, can be modeled using linear algebra. So it's a pretty broad formulation of things, and that should get us thinking. At least I think. Anyway, that's this is something to think about. And if you want to talk about it more, head on down to the Centaur Courses, and I'll see you there. All right.